Hello everyone. In this video, we are going to evaluate an interesting integral. So as you can see, we are supposed to integrate this function that is 1 over 1 plus tan x, and tan x is raised to an irrational power over here, isn't it? And this is a definite integral because we are integrating from 0 to pi by 2. Okay. Before we proceed to the solution, I would advise you to give this problem a try by yourself, and later on you can come back and watch the solution, because if you try by yourself it will be more interesting while you watch the solution, right? Yes. So let us dive into the solution. I hope you tried this one. So what is the technique that we are going to use? Now, first of all, I will write this as it is, 0 to pi by 2. So we are going to integrate this function, that is 1 over 1 plus tan x, right? So 1 plus tan x. Now tan x can be written as sin x over cos x, right? So I will write tan x as sin x over cos x. And we are going to raise this to the power root 2, and I will write dx over here. Okay. Now you can distribute this root 2, the exponent, to sin x and cos x separately, isn't it? So we'll do that. So this is equal to what? 0 to pi by 2, 1 by, so 1 plus sin x to the power root 2. So we are going to distribute the power separately. Sin x to the power root 2 divided by cos x to the power root 2, and we keep dx as it is. Okay. Now I have a complex fraction over here, right? So we have 1 by 1 plus sin x to the power root 2 by cos x to the power root 2. I don't want this term here in the denominator. This makes simplification difficult, right? How do we get rid of that? It's very easy, right? So get rid of the denominator. We just have to multiply this entire term with that particular term, that is cos x to the power root 2. So we'll multiply this, but when we multiply the denominator with something, we make sure that we multiply the same thing with the numerator as well, so that there is no change that is made, right? Yes. Now let's multiply. So here, as you can see, cos x to the power root 2 times 1. So we have to multiply to each and every term. It's just cos x to the power root 2, right? So we'll write the new integral now. So this is equal to 0 to pi by 2, and on the numerator we just have this cos x to the power root 2 divided by cos x to the power root 2 times 1 is nothing but the same thing, right? Cos x to the power root 2. But plus, when you multiply this with the second term, what happens? This and this will get cancelled out, right? So we'll just have sin x to the power root 2 remaining, dx. Okay. Now we have started from this function in the beginning, that is 1 by 1 plus tan x to the power root 2, and we have reached this one, right? So maybe I would like to call this one as I. Okay, let me call this as integral I. We want to evaluate this definite integral. Now to evaluate this complex looking fraction, I want to use one of the very interesting properties of integrals. So what is that property? So that property is, whenever you integrate from, let us say, 0 to a of f of x dx, this is the same as 0 to a, and we can just replace the x with a minus x. Okay. So I hope you know how to prove this, right? So for those of you who don't know the proof, I will give you the proof briefly, but if you know the proof, you can just skip this ahead and go to the next step. So we want to prove this property of definite integrals. So what have we done? We have replaced x with a minus x, right? So replacing is same as substitution, isn't it? So what are we going to do in this integral? We are going to substitute x with a minus x. So I'm just going to substitute. I'm going to replace x with a minus x. So what happens if you differentiate on both sides? So maybe I'll just put the equal to sign there. That's better, I think. So we are substituting x with a minus x. So instead of x, maybe we can go for some other variable, right? Anyway, at the end we can just change it back to x. Okay, they are just dummy variables. So I will substitute x as, let us say, a minus u. So when we differentiate on both sides, we get dx is equal to differentiation of a is 0 and differentiation of u is minus du. So now you know why I did not use x over there, right? If I used a minus x, then I will get minus dx. So dx equal to minus dx will not make any sense, right? Yes. Now let us go back and back substitute in this one, that is integral from 0 to a of f of x dx. This is the left hand side part. So this is equal to what? Integral from 0 to a but one more thing to notice here, that is 0 to a was when we were in the x world, right? Now we have changed into the u world, that is these limits are from x equal to 0 to x equal to a, right? So this is from x equal to 0 to x equal to a, but we have to convert these limits into u world, isn't it? And it's very easy, we can do it here itself, right? So from here we want to calculate what is u, right? So here we know that u is nothing but a minus x, right? Now when x is equal to 0, what is u? When x equal to 0, u is a minus 0, that is nothing but a. Similarly, when x is equal to a, that is the upper limit, u will be a minus a, that is 0. So we'll change the limit. So now it will be from u equal to a to u equal to 0. So now we have got f of x will be a minus u. I'm replacing x with u, and dx will be minus du, right? So we have a negative sign over here. And how do we deal with negative sign? Actually, it's pretty much easy to deal with it, because if you want to just remove the negative sign, you have to just change these limits, okay? Just reverse these limits. So now it's from 0 to a to 0, right? So you just make it 0 to a, that's all. So if you make this from 0 to a, then the minus sign will vanish, okay? That's also one of the properties of integral. So we have f of a minus u du. Okay, so now we started from f of x dx, right? So now we have arrived it here. I want to arrive at f of a minus x, not u, right? And we can easily do that, because according to another property of integrals, we can always change the variables. Okay, this u can be changed to x anytime. U is just a dummy variable, x also is a dummy variable, we can change them, there is no problem with that. So we have 0 to a and f of a minus x dx. So we are just replacing u with x, because it makes sense. When you differentiate u, you get this equal to dx itself, right? So there is no change that is done if you replace u with x. So that this is how we can prove this property. Now let's go back to the problem to evaluate the integral. So here we have this property which we are going to apply to this I. Okay, so what are we going to do? I is equal to 0 to pi by 2. So here we have 0 to a, right? When we have 0 to a, we replace x with a minus x. Since we have 0 to pi by 2 here, we replace x with pi by 2 minus x. Okay, replace this with this. That's all. That's what you are going to do. So what will happen? Cos x will become cos of pi by 2 minus x. And this will be raised to the power of square root of 2. And divided by, do the same thing in the denominator as well. Cos of x will be replaced with pi by 2 minus x, and this will be raised to the power root 2. Do the same thing here as well. Sine of pi by 2 minus x and raised to the power root 2, and this will be dx. Now let's evaluate this. What is cos of pi by 2 minus x? It's nothing but cos of 90 minus x, right? So cos and sine are complementary, because you know the name itself, right? Sine and cosine. So co means complementary. It's complementary of sine. So we already know this, right? So that is cos 90 minus theta is nothing but sine theta, right? Same goes for sine as well. That is sine 90 minus theta is also equal to cos theta, right? Because sine and cos are complementary. Whenever the angles here add up to 90 degree, we call them as complementary angles, right? So whenever we have complementary angles, cos and sine will be equal. Cos of one angle will be equal to sine of the complementary angle. Okay, we are going to use that property. So if we are pi by 2 here means 90, that's all. So I will be equal to 0 to pi by 2. Cos pi by 2 minus x is nothing but sine x. Sine x to the power root 2 divided by, this is nothing but sine x to the power root 2 plus Sine of pi by 2 minus x is nothing but cos x to the power root 2 dx. Okay, let me call this as result number 2. If this is result number 2, then what is result number 1? Let me go back. So here we have this expression here is result number 1. You can observe that this expression and the expression that we have here resemble the almost resemble each other. But one thing is that here in the numerator we have sine x to the power root 2 and here we have cos x to the power root 2. So let me bring this equation number 1 as well so that we can analyze them better. So here we have the result number 1 as well. So what are we going to do? We are going to add result number 1 and result number 2. So we are going to add them up. Okay, so what will happen if you add the left hand side part, that is I plus I, it will become 2I, right? On the right side, as you can see, both the integrals are having the same limits, right? That is 0 to pi by 2. So there is no problem in adding this inside part. So we'll just have the common 0 to pi by 2 and we'll add these two integrals. You can see both of them have the same denominator, right? Same denominator. So we will keep the denominator as it is. It's like adding fractions. So we keep the denominator as it is, sine x to the power root 2 plus cos x to the power root 2. Add the numerators. So here the numerator is this and here the numerator is this. So we are just going to add them up. So what will happen? The numerator in the first integral is sine x to the power root 2 plus in the second one it is cos x to the power root 2. So what do you see here? Same numerator and denominator. That means we can just cancel them out and this entire complex integral just reduces to 1, right? So let me scroll down. So we get 2I is equal to 0 to pi by 2. So this is just 1 dx, right? It's just 1 here. And we know that integral of 1 is nothing but what? X, right? So it's x, but we have to evaluate this from 0 to pi by 2. That's very important. So put the upper limit first, that is pi by 2, minus the lower limit, that is 0. So 2I is nothing but pi by 2. So which tells us that the value of the integral I is nothing but pi by 4. So what was I? I was the integral that we started with, right? That is nothing but, if you go back and see here, this problem, right? This itself is I, because this one is just a modified version, right? That is equation 1 is just a modified version of I. So the value of I from the evaluation is nothing but pi by 4. So I hope all of you enjoyed the video and liked the solution. For more such interesting videos, subscribe to my channel and I will see you all in the next video.